Thank you. Welcome to the talk. So we will be talking about unstructured data and scaling unstructured data with Anyscale and Data. Before we dive in, just want to introduce myself here. I'm Praveen. I'm from Anyscale. I lead engineering team here. I also have with me my teammate Hao.
Good afternoon, everyone. My name is Hao. I'm a tech lead on Data team, and also I'm like one of the earliest contributor to a RE project. So before Anyscale, I led the recall team at the N group, and that supports the world's largest redeployment. Yeah, nice to meet you.
All right. So the rough outline of the talk would be, I want to give you a brief overview of the patterns we are seeing in unstructured data use cases in the industry, and also introduce some of the technical challenges we see when people tend to scale these unstructured data use cases. And then we claim Ray data as a solution and show you how Ray data achieves that. The rest of the talk, we would be deep diving into the architecture of Ray data and some of the optimizations we see on Ray data on Anyscale, which we call as Ray Turbo, which you might have heard in the keynote and other talks. And then we do have a case study of stable diffusion data processing, wherein you can see all the tools that Ray data provides and observability, scaling, and performance. We would go through that in the case study. So with that, let me get started with the use cases for unstructured data. So unstructured data, so why do we care about unstructured data? The first main use case is pretty intuitive. We have been seeing this for over a decade now, basic object detection in images. But then over the recent years, we have seen more use cases of unstructured data. Like for example, in the field of medical industry, in the field of healthcare, we do see a lot of analysis on images and other data. And then geospatial data brings a different dimension to unstructured data. You can imagine all the industries that have recently propped up, like ride-hailing industries or like automotive industries, or even like people using geospatial data for niche use cases like studying crop cultures or other use cases, even like oil wells and other stuff. And then a recent pattern that we are seeing is also on manufacturing and manufacturing quality. There is a lot of insights and data collection that is happening on manufacturing industry. And then robotics. We see this includes human robots, but also things like self-driving cars, wherein there is a lot of like perception models, which are usually run on point clouds or LiDAR data or even image data. All these use cases are just the beginning, but this also shows us that unstructured data is going to keep increasing everywhere, and it is going to be in all use cases we see. Now, what are some of the challenges that we see when we run these unstructured data workloads in traditional data pipelines and data systems? One of them being heterogeneous compute. These unstructured data processing pipelines are almost fundamentally always involving multiple compute resources like CPUs and GPUs. Here I show a simple example of a very simple unstructured data processing pipeline which has 3 stages. As you can see, the third stage has a GPU inference and the first 2 stages are mostly CPU bound. This is quite common in most unstructured data use cases. What we do see when you use traditional data pipelines or data systems is a lot of compute resource misutilization. In this picture, you can see the red line which shows that even though some batches of data, which are those blue squares, have finished some processing on the first 2 stages, we haven't yet put the GPUs to utilization to work. This is a big usage, suboptimal usage, which we think can be solved in a better way. The other problem that we see is pure scale and reliability issues. One is obviously because this unstructured data has a lot of explosion of unstructured data definitely increase the scale of the data we are processing, but also the patterns are different. Because these unstructured data processing also involve a lot of heavy GPU usages, it's pretty common for people to use spot instances in order to run these pipelines, which means preemptions or failures are very common. So instead of thinking fault tolerance as a fail-safe mechanism, you have to think about this as a first-class citizen. Fault tolerance becomes a first-class citizen in these pipelines. Next is the sheer complexity of the ecosystem. On one end, you see in this unstructured data pipelines is different data sources, different formats of data, predominantly with no defined schema. On the other end is you see a traditional ML ecosystem like your training systems or your like ML inferencing systems. Today, existing solutions are very fragmented. You don't have one system which can bring you from one stage to the, which can run through all the stages of this pipeline. We claim that Ray Data helps solve all these problems. And in order to, as you can see from this picture, Ray Data can help solve the heterogeneous compute problem by an innovation called streaming execution. What we can do with this is we are able to maximize the resource utilization at every stage of the pipeline. We don't need to wait for every stage to be finished before you start putting your compute resources in the next stage to use. This helps you maximize your GPU utilization and also reduce the cost. Next is scale and reliability. We designed this system with fault tolerance as a first-class citizen. Especially on Ray Turbo, we have implemented a lot of proprietary checkpointing and resumability features, which you will see later, which will help you recover and run this platform regardless of failures at any stage. And also on partial failures, the system just seamlessly continues. On full failures of like a driver node in this case, you would be able to seamlessly recover without having to restart the job at any stage. And then because Ray Data is built on top of Ray, it gives you a really flexible and performant API. And being Pythonic in nature means that it integrates seamlessly into all the ML ecosystem. What this means is you will be able to, in single code and a single pipeline, be able to run your entire data processing, inferencing, or even training pipeline. You don't need to have to checkpoint the solutions and have to come up with a different framework for doing the next stages of your pipeline. You can do all of this in a single simple pipeline, and that is available on Ray Data. Before we go into Ray Data deep dive and APIs, let me go through some use cases. We have been seeing a lot of usage of Ray Data in the industry. You might have heard some tech talks about it during the course of the summit. I picked up some of those, like Amazon has been using it. You might have seen it in the keynote. They have got up to 90% efficiency using Ray Data on Ray Data. Roblox has been recently using this data, and they have tremendously benefited from this. Pinterest is another massive user of Ray Data on open source. They have been running this tool for their GPU-based models, and they have seen a lot of benefits in both in terms of usability and also in terms of performance. Let me give you a peek into how Ray Data allows you to express these pipelines. At the core, Ray Data has simple read and write operations. Like I said in the earlier slide about flexibility and support in the ML ecosystem, it supports read and write from a lot of different data sources and a lot of different formats. In fact, on Ray Turbo, we have even optimized some of these reads and writes for unstructured data like images and videos, and we do provide proprietary extensions for those. And Ray Data, once you read the data, the fundamental object that you get is a data set on which you can do any kind of data transformation. You can do data transformations row by row, like filters and maps, but also Ray Data provides you a way to run these operations in batches, which is much more performant. For example, map batches can be done on a row of data at a given time. In some cases, it's a lot more performant than doing a row by row operations. And we provide all the consumption operations like show, take, all these operations which extract the data at the end of the pipeline. And then we also have aggregations. On Ray Turbo, we also provide streaming aggregations, meaning you'd be able to stream stream different operators and aggregate them. And one of the innovations of Ray Data, because it is built on top of Ray, is it allows you to express compute resources easily. So you can specify your concurrency, you can specify your compute strategy, you can specify whether the operators have to be using CPUs and GPUs. What this allows you to do, it allows you to scale different stages of pipeline in different compute resources at different concurrency. This is super powerful. I'll show, as you will see later in the talk, this is super powerful when you have to maximize the utilization of compute resources at different stages. And then we have a lot of integrations to ML ecosystem. For example, we have integrations with PyTorch, we have integrations with TensorFlow. Again, this goes back to what I said in the previous slide. It allows you to seamlessly integrate this pipeline end to end. This is a simple example putting together everything I've shown so far. What you see on the left is a simple code to do like a three-stage data processing on image data. The first stage is just a simple CPU operation, which is just resizing. And the second stage is segmentation model, and the third is a classification model. As you can see in the API, you're able to express the concurrency of each operation easily with a simple line of code. And at the same time, you're also able to tell where each of those operations needs to run and how much compute resource it can utilize. If you see the right side of the picture, you will see that each of those is a different stage, each of which is scaling at a different level. Like one of them is scaling to 4 actors and another one to 8 actors, and each of them is able to perform, and all the data is transferred from one stage to other stage in a streaming way. That way you don't need to wait for one stage to completely finish before the next stage starts its work. This maximizes utilization, so all the stages are working concurrently. To show you how all of this is done under the hood, let me bring in Hao, who will walk you through the architecture of Ray Data.
Okay, thanks, Praveen, and hello, everyone. In the next section, I'm going to dive into the internal architecture of Ray Data and explain how Ray Data resolve the technical challenges we mentioned earlier with some key innovations. So first of all, let's take a look at this simple example of batch inference. So we have a pipeline of 4 stages. So when running this code, the first thing Ray Data is going to do is to convert the user code to a logical plan. So basically, logical plan consists of several logical operators that define what to do for each stage of data processing. And we can see we have 4 operators here. So read, transform, inference, and write. So among these 4 operators, only the inference operator uses GPU resource. So this is because we have set number GPUs to 1 for it. And other operators, by default, only use CPU resource. And the next thing Rita will do is to convert the logical plan to a physical plan. So basically, a physical plan consists of multiple physical operators that define the concrete implementation of how to process the data. And also by converting the logical plan to a physical plan, the plan will also be optimized. For example, in this case, we can fuse the read and transform together as one single physical operator because they both only use CPU resource. In Ray Data, the basic unit for data processing and data transfer is called a data block. So basically, for each operator, they process input data blocks and generates output data blocks in a streaming manner. And each operator is also associated with an output queue to buffer the output data. So the operators are running on the driver of your job, but the data will be stored in the distributed Ray object store. So by using the object store, so the operators doesn't need to fetch the data to its local process. It only needs to manipulate the object references to the remote objects. And to perform the actual data processing, and Ray Data use Ray tasks and actors. And users can specify different resource requirements for these actors and the tasks. And Ray will schedule them to the node with the corresponding hardware in the cluster. And at the core of Ray Data, there's a central decision-making component called the streaming executor. So basically, the streaming executor is responsible for scheduling tasks like managing resources and handling back pressure. And one important thing to notice here is that in Ray Data, all the tasks are scheduled dynamically at runtime. So by doing so, Ray Data can ensure all the GPU operators are consistently saturated. Let me explain why. So let's say in this case, if the inference operator, GPU operator is undersaturated, when Ray Data found this, it will simply schedule more tasks for the first stage, the load and transform operator to output more data and then feed into the map operator, the inference map operator. Okay, and now let's wrap up the architecture and check out what advantages we get from this architecture. So firstly, with the streaming execution engine that supports back pressure, Ray Data can easily support data set up to petabyte scale of data. And secondly, because of thanks to this heterogeneous resource scheduling and dynamic task scheduling, Redata can fully utilize all the GPU resources in the cluster. And thirdly, because Redata is built on top of recall, we leverage recall's lineage reconstruction feature to handle failures. So basically, when a task crashed in the middle of execution, this feature will automatically resubmit the task. And lastly, the object store also brings us some additional advantages. For example, for workers running on the same node, they can share data without copy using the shared memory. And for workers across different nodes, the object store can efficiently transfer data from one node to the other. And also the data transfer will be pipelined with the task execution. And last but not least, if the buffer queue size has exceeded the memory limit of shared memory, the object store will also automatically spill the additional blocks to disk, avoiding auto memory errors. So besides all the features we have mentioned, I think Anyscale also provide improved Redata solution that we call Retable Data. So basically, Retable Data comes with some more advanced features that makes the unstructured data inference jobs even faster and cheaper at large scale. So first of all, speaking of performance, one of the biggest pain point for many beginner users is to optimize the configuration. So basically, if the configuration is not correctly set, it can lead to some performance or even reliability issues. For example, low GPU utilization, under parallelism, or high memory pressure. So Retable Data offers a configuration optimizer that can automatically detect some common issues and propose suggestions to help users optimize corresponding configurations to fix these issues. And another issue in our observation is that when you have a huge data set that consists of many small files, the metadata fetching stage can take significant time because it's blocking. And this will usually slow down your development cycles and also cause resource waste. So to deal with this issue, we recently shipped a new feature that allows fetching metadata in an incremental way. So by doing so, the job can kick off the actual data processing tasks immediately when it starts. And with this feature, we have seen up to 4.5x shorter job startup time in our benchmark tests. The second area we are improving is fault tolerance. So first, as we have mentioned before, so thanks to the lineage reconstruction feature, so if a node gets preempted, and the tasks running on it will be automatically resubmitted to a different node. So this feature allows the job to continue to run without crashing due to a random hardware failure. But when you are running your job on a large-scale Spot instance cluster, when many nodes get preempted at the same time, it can still lead to performance degradation. This is because the node preemption and the task resubmission are transparent to Redata streaming executor. So because of this, some performance issues can happen. For example, the resource contention between the regular tasks and the retry tasks, and also the resource accounting on the streaming executor will be inaccurate. So to address this issue, Retable Data offers a failure-aware scheduler that can make better decisions about task scheduling and back pressure during node preemption, and also making sure the job always running at the optimal performance. So despite this automatic task resubmission, so in certain scenarios, you still need to rerun your job. For example, when you want to update your user code to deal with some edge cases in your input data, or when the head node or even the entire cluster crashes. So to avoid restarting the job from scratch, So Anyscale provides a job checkpointing feature that will automatically checkpoint the progress of the job and resume the progress when rerunning the job. And lastly, speaking of scalability, Anyscale provides an enhanced autoscaler that allows the job to start with 0 resource and efficiently scale up to thousands of GPU nodes. And also support dynamic scaling down. So with this feature, you can even shift resources among different jobs at runtime. So to enable this feature, users simply need to set the cluster size and the concurrency of the operator to a range. Okay, in the last section of this presentation, let's walk through a concrete example to demonstrate how to use read data to deal with a real-world problem of unstructured data inference. So the task we are going to implement is the data preprocessing pipeline for stable diffusion chaining. So this picture shows the model architecture of the stable diffusion model. So we can see from the picture that the model basically takes 2 types of inputs. One is the image latency, and the second is the text embeddings of the corresponding captions. So what we are going to do is to implement an offline pipeline to pre-compute the image latency and the text embeddings for more than 1 billion samples. So to implement this with read data, so we also define such a typical 4-stage data pipeline. So first, we use the read packet API to load the raw image and the text data from cloud storage. And then we use a map function to apply image transformation to information and text tokenization. And thirdly, we use map batches to apply the encoding logic to the data using GPU resource. And lastly, we use write packet to write the results back to cloud storage. So if you want to learn more about the full example, there's a free template on Anyscale covering all the entire job of stable diffusion chaining, including how to use read data and read chain to do online and offline data processing and distributed model chaining. And we also published a blog post like a while back covering more technical details. Check it out if you are interested. So when running the job on Anyscale, so Anyscale and read data also provide some observability tools to help you better understand what's going on under the hood about the job. So the most commonly used one is this progress bar. So basically, it shows you some real-time key metrics about the job, as well as for each operator. And if you want to view the historical data of the metrics, there's also a Grafana dashboard that shows several time series metrics charts of both at the record and read data level. And also, if you want to dig into a specific task or worker, you can click a button on the read dashboard at runtime to generate such a flame graph, CPU flame graph, so you can get a sense of like which function is the most expensive one. Okay, lastly, let's take a look at some key metrics of this benchmark. So first of all, we can see that this job can fully utilize the GPU resources across the entire cluster. And also, the cluster can scale up pretty quickly within a few minutes when the job starts. Last but not least, the throughput of the job can scale up linearly with the number of GPU nodes in the cluster. Okay, so at the end of the presentation, let me do a quick summary of the key takeaways. So first of all, read data resolve the key technical challenges with some key innovations: the streaming execution engine, heterogeneous resource scheduling, automatic failure recovery, and the Python native API that allows you to seamlessly integrate your read data code with the existing ML ecosystem. And on the Anyscale side, Anyscale provides a fully managed platform for read data and any read workloads. And Anyscale also provides a more advanced Retable Data solution that makes unstructured data inference even faster and cheaper at large scale. Okay, I think that's what we have today. Thanks.
All right, so we have about 4 minutes for the Q&A section. If you have any question, please raise your hand and wait for me to bring the mic to you. First question.
Thank you for the presentation. So I'm interested in learning, like, how do we handle the back pressure internally?
Okay, the question is how do we handle the back pressure internally? So basically, the streaming execution will keep track of the resource usage of each operator, and we allocate some budget. So basically, we check how much resource we have in the cluster, and we allocate the resource to each with budget to each operator, and basically the streaming execution can decide how many tasks to submit and whether it needs to pause a running task based on the runtime resource usage. So that's how it works at a high level.
Next question.
Hi, yeah, great talk, thanks. Do you ever see problems where the head node starts to become a bottleneck? Because there's I think my understanding, and this might be wrong, is that all the communication has to go through there at some point.
Yeah, okay, good question. So the question is whether the handle can be a bottleneck of the job. So I think for most batch inference jobs, I think because we are doing streaming execution, also first of all, let me explain. So the overhead on the handle is mainly about the streaming executor. If you need to manage all the object references of the entire cluster, but for batch inference, unstructured data batch inference jobs, I think that's usually not a bottleneck because we are doing data processing in a streaming way, so we don't have too many blocks in memory at the same time. But if we are doing there are other more memory intensive operators, like for example group by. So for those operators that's not streaming, you need to keep all the object reference in memory. For those workloads, the handle can be more expensive, can be more of the bottleneck.
Would the load on the head node scale with the number of GPUs, for instance? Have you gone to say if you get to hundreds, 500 GPUs, does that load start to?
Yeah, I think in our experience, I think one handle can easily handle more than 1,000 GPU nodes. So that's usually not an issue. I think if you find this bottleneck, I think the simplest way to use a larger head node.
Got it. Thank you.
Next question. Can you help?
Regarding the observability, do you have a way to visualize the DAG of your execution, just like a Spark DAGs?
Okay. We currently don't have the DAG visualization on the dashboard, but we will print out the DAG shape in the console. So I think you can kind of get a sense of that.
We have time for one more last question.
Hi. So regarding the task retries, so let's say if you have a long-running batch job, right, and for a week, and one of the tasks fails. So you said that on the open source version also you have task lineage. So can that reconstruct the entire task from the beginning and get it rerun that particular task? I think in the same context as Spark, right? Like Spark, if you have one task failure, it will have that lineage and it will bring that task in the end, unless there is I think it tries 3-4 times unless there is a task failure or on application level. So
Okay.
Can that be done on open source version? And if no, then is that something you solve on the proprietary version?
So if I understand your question is when a task fails, can we trace back to the previous previous tasks in the lineage, right?
Yeah. So let's say we have multiple
multiple
batches, right?
stages, yes.
And
yes.
one of them fails.
Yeah,
right?
that's
so now,
on open source, yes. So basically, that's how lineage reconstruction works. So basically, when a task fails and if the object's lost, we can trace back to the previous task in the lineage and rerun the task to reproduce the object.
Okay. Cool. Thank you.
All right, so if you have any more questions, please ask Hal and Praveen after the talk. We are out of time. And please give another round of applause for Hal and Praveen. Thank you, everyone.